Okay, so welcome everyone, and it's great that we are back almost to normal with this colloquium. Of course, we are having this on hybrid mode, and there are some of you who are joining us online. So welcome everyone to this new format, and hopefully this would stay this way and get better, and we would go back to our usual in-person colloquium. So today it's great pleasure, special privilege for me to introduce my colleague, Pranav Pandit, who is a faculty at ICTS. And Pranav has been at ICTS since 2018, and his research is related to understanding various mathematical structures of quantum field theories, and something that he would discuss in detail today. Pranav did his PhD from University of Pennsylvania, and after that he was postdoc in Vienna, and since 2018 he has been at ICTS. So today he would be talking about geometry of the quantum geometry. So Pranav.
Thanks a lot, Subro, for the wonderful introduction. And thanks a lot for the introduction, for the invitation to give a colloquium talk. It's really a pleasure and privilege to give a colloquium talk here at ICTS. So I should say a few things before I get started. Also, this is my first in-person talk during this pandemic. So thanks for that also, Subro. We're really lucky to be here today. And I hope Omicron doesn't throw us all off and send us back to square one. Let's keep our fingers crossed. A few words before I get started. So this is a colloquium talk, and it's addressed to people from different departments. So it's supposed to be accessible to beginning physics students and biologists. I'm a mathematician, but this talk is supposed to be accessible to everyone. So it's not, no math background should be necessary for at least a good first half of the talk. So don't hesitate to ask questions if you have any. Yeah, great. So let me get started. So here's, I'm going to talk about a kind of geometry, a new kind of geometry, relatively new in the history of mathematics. So to put it in perspective, I want to start by giving you some snapshots from the history of geometry. And necessarily these will be just brief snapshots from different times. After that, I'm going to spend a lot of time talking about this equation d squared equal to 0. Okay. So I'll let you take that in for a moment. A lot of this talk is going to be about that equation. I thought really hard about finding one equation that would sum up all the things I'm talking about, because math is supposed to be about equations. And that's what I came up with. So let's see how that goes. And then I'm going to use that to tell you about geometry in higher categories, whatever that means. So by that time, you will know what a higher category is, or at least one kind of higher category. I'll tell you what it means to do geometry in this. So that was one equation that sums up my talk. One thing that I will tell you by the end of this talk is the equation d squared equal to 0. Another thing that I'll tell you about is this picture. So my talk is all about taking points and replacing them by one-dimensional objects. And there are only two interesting compact one-dimensional manifolds, the interval and the circle. If you're a physicist, you may want to call this an open string and a closed string. And the idea here is that geometry has always been about shapes. And when we talk about shapes, we think of them as composed of points. And I want to talk about a kind of geometry where there are no points, where it's built out of something else. That something else has to do with strings, oscillating strings. Let's get started. So if you go back to like 300 BC, I think it was, when Euclid was around, you might have seen people doing geometry with these kind of figures. They had triangles, circles, lines. And these were elementary building blocks, right? So you didn't really know what a line was or what it was composed of. A line was an elementary building block. Circle was an elementary building block. And Euclid had the great, was one of the first people, or the first person that I know of, that tried to axiomatize the rules that these animals are supposed to follow, the circles, the lines, and so on. And he said, whatever these are, they follow these rules, and let's see what we can make of these rules and what we can deduce from them. And those rules weren't just made up out of nothing. They were made to explain physical things, things that they observed in the world around them. They were either building stuff or measuring their farms or whatever it was. And presumably the things that they were allowed to take for granted were things that they experientially observed in the world around. But of course, if you jump, throughout the history of mathematics, one of Euclid's postulates, which is the postulate that two lines which make less than a right angle to this line will meet at some point, that has always been viewed as being on shaky ground throughout the history of mathematics. There are lots of people who challenged that axiom and wondered whether it really represents the real world. And of course, now we know that it doesn't, in the sense that you can have shapes, geometries, where the rules of Euclidean geometry fail. For example, the angles of a triangle may not add up to 180 degrees. All you have to do is walk on the surface of the Earth to find a triangle where that happens. Or in this picture, you see angles where the triangles where the angles add up to less than 180 degrees, and that's the hyperbolic plane, of course. So that was one era of geometry, and to sum it up, it was a synthetic kind of geometry where the basic objects were some given objects, lines, circles, and so on, and they obeyed certain rules. It took a really long time to get to the kind of things that we take for granted today, where you write coordinates to represent your points, and you write equations to represent your shapes. And that was thanks to Descartes, who invented the Cartesian plane and wrote equations for things. And of course, Newton introduced one more element into that. He said you could study the infinitesimal properties of those shapes by looking at the derivative. He invented the calculus for this. Right? And that was in the 17th century. And that we take it so much for granted, but it completely revolutionized the way we think about geometry. I'm not saying this is a better kind of geometry, it's just a different way of doing geometry. And it opened up geometry to algebraic tools and analytic tools, because now you could study things by using equations. Okay, so let's jump to Riemann. So I'm skipping a lot of history, obviously. This is not a lesson in the history of geometry. But Riemann, following ideas of things that Gauss and others had discovered, made another tremendous leap. He said that a shape doesn't have to be sitting inside some Euclidean space. You could be an ant living on the surface of the Earth and moving around on the surface of the Earth. And for you, the third dimension may not be relevant, and you may make measurements on the surface. And all you need to know is that you have local coordinates inspired by Descartes, where you can measure things. You can measure length, for example. And those local coordinates should transform. If I have one set of local coordinates and you have a different set, they should transform according to certain rules. And that gave rise to the idea of a manifold. And that was, again, revolutionary, because without it, I don't know if general relativity could have existed, because it's basically saying that our space-time, you don't have to think of it as sitting somewhere else, for example. Something that people know less about is that Riemann actually speculated that space-time may fundamentally be, physical space-time, may fundamentally be discrete, or a mix of discrete and continuous. So long before quantum mechanics was discovered, I don't know how, based on what intuition, he briefly speculated on it and then said, okay, but that will take us in a different direction, and we're not working on that right now, so let's put it aside. I just thought I should mention it. So coming to Riemann geometry, here's a picture of a manifold. I've drawn the surface of a bagel, and this bagel is going to be my everything bagel. It's going to appear many times in this talk, just because mathematicians like to take the simplest thing that demonstrates everything they want to talk about, and that's the simplest thing that I could draw. I mean, already drawing in LaTeX is time-consuming and challenging enough, and that's my limit when it comes to drawing in LaTeX. So there we go. So we have the surface of the bagel, and but this could be any Riemannian manifold. And what makes it a Riemannian manifold is that you have a metric, which is a way to measure length. And the way you measure the length is the manifold has something called a tangent space, which is the infinitesimal displacements at a given point. And again, the important thing that Riemann realizes is that you don't need to put your space into some ambient space to define that. And you can define the length of a tangent vector. That's what the Riemannian metric is. At each point is given by giving an inner product on the tangent space. And this inner product is, as you all know, symmetric. And the length is defined as the integral of the velocity, of this expression. Now, this idea of length in geometry and distance is well known. We all study length in school and so on. But there's another kind of geometry that is less well known that started around the same time and is perhaps as important, if not more important, in describing most of physics, which is symplectic geometry, where area plays the fundamental role. You don't have a notion of length a priori, but you have a notion of area. And that area is given by, well, if I have a small parallelogram in my space, I should be able to measure the area of it. So it should give me, for a pair of vectors, I should have a number. But if I reverse those vectors, the order of the vectors, the orientation of the parallelogram switches. So the area should switch in sign. So omega should be a skew symmetric form. And the way you compute the area of some surface is to integrate omega over that surface. This is almost the definition of a symplectic manifold. You want omega to vary smoothly over the manifold, just like you want the metric. It's a little more subtle. I'll define it in a moment. But before I give the rigorous definition of a symplectic manifold, let me just say one thing about why it's so important in physics, symplectic geometry as much as Riemannian geometry. Here's the reason. Let's take our bagel and let's map it to the real line by some function h, which maybe you want to interpret as a Hamiltonian. Now, if you have a function, you can compute its derivative, dh. Now, what is dh? dh is an animal that takes a velocity vector. It takes a vector and tells you the rate of change of the function in the direction of that vector. So dh takes vectors as input and spits out numbers. That's what dh is. In school, we're often told that the derivative of a function is a vector field. It's not. This is what it is. It takes vectors as inputs, and it tells you the rate of change of the function in the direction of that vector. Now, if I have a Riemannian metric, then I can ask, is dh of blank the inner product with some vector grad h? And because the Riemannian inner product is non-degenerate, there always exists such a vector, and that's what we call the gradient. So to even talk about gradients, you need to fix a Riemannian metric. But the game I just played with the gradient, I could just as well play with with G. I could play with omega. I could ask, is there a vector x sub h such that pairing omega x sub h with something gives me dh of something, of that something? And that is called the symplectic gradient, or also known as the Hamiltonian vector field generated by this Hamiltonian. So anytime you have a function, if you have a Riemannian metric, you get a vector field, a gradient vector field. And if you flow along the gradient vector field or the negative gradient vector field, you decrease h as fast as possible. So dissipative systems are described, all dissipative systems are at least locally described by this kind of, by taking a gradient of something. On the other hand, if you have a conservative system, it turns out you can easily prove just by elementary calculus that if you construct x sub h from the symplectic form in this way, it must point along the level sets of the function h. So it preserves the Hamiltonian, and essentially all Hamiltonian systems, all conservative systems have this nature. You don't need to put too many hypotheses in to deduce that your system should be described by a symplectic form. So whether you're talking about classical mechanics, orbits of planets, flowing incompressible fluids, you're basically talking about symplectic manifolds and their geometry. So on this board here, you have a lot of physics. On the right, you have the heat equation and all those dissipative systems. On the left, you have all the conservative systems you can think of, and real life is some mix of it. And of course, Riemannian metrics also enter into as a dynamical variable in describing relativity, but that's a different story. Yeah. It's whatever vector has the property that omega xh paired with something is the same as dh acting in the direction of that vector. So omega xh of some vector u should be the rate of change of h in the direction of u. That's the definition. And there's a unique such thing because omega is non-degenerate. Yeah.
Just to make an announcement. So everyone, please try to use a microphone. Otherwise, people online cannot hear the questions. Okay. Okay. Sorry, Pranav.
Okay. So here's a sort of formal slide. I just wanted to put in the definition. So I'm not, just hand waving the whole time. I will be hand waving quite a bit, but so the definition of a symplectic manifold is that it's a smooth manifold with a non-degenerate 2 form. A 2 form is basically what I defined for you. It's something that it's something that you can integrate over a 2-dimensional submanifold to get a number, which is like an area. And it should satisfy this additional condition that I didn't mention earlier, which is that d omega should be 0. The exterior derivative of omega should be 0. And physically, what this translates to is basically saying that if you flow along the Hamiltonian vector field, the laws of physics don't change. The Poisson bracket itself doesn't change. So that's what a symplectic manifold is. Now, what's a Kahler manifold? A Kahler manifold is something that combines a symplectic structure with a Riemannian metric. Turns out that you can also describe it as something that combines a symplectic structure with a complex manifold structure. So complex manifold just means something that locally looks like Cn, right? So you can put complex coordinates on the space, and the change of coordinates from one to the other should be holomorphic, analytic. So if you have a complex manifold, then you can define this operation I, which is each tangent space becomes a complex vector space. So you can define a map I from every tangent space to itself with squares to -1. This is basically multiplication by square root of -1. Right? So that's what I mean by m comma I. So it's a complex manifold, which also has a symplectic structure, such that when you take omega of I blank, omega of I u comma v, this thing is symmetric automatically because I squared is -1. You can check that. And that symmetric thing should be a Riemannian metric. It should be non-degenerate. That's what a Kahler manifold is. Okay? So it's something that has a compatible triple consisting of a symplectic form, a Riemannian metric, and a complex structure. Okay, anyway, so you can forget that formal definition. Here's how most Kahler manifolds arise. If you take the zeros of homogeneous polynomials in projective space, and never mind the bit about projective space if you don't know what that is, if you write equations like this, and look at their zeros, then those, they may have singularities, but if it happens to be smooth, which will be the case generically, then the resulting thing is a Kahler manifold. Here's a picture of a Kahler manifold, a complex 3-dimensional, real 6-dimensional manifold. Obviously, you can't draw something 6-dimensional. So what this really is some sort of projection. You take a slice of that 6-dimensional thing and then take its the real solutions to the equation, and you already get something this complex with this equation. It's a very famous Calabi-Yau manifold, and I got this picture from Wikimedia Commons. Okay, so I'm going to draw very simple pictures, but you should keep in mind that even the simplest equations give you tremendously complicated spaces in terms of their shape. Okay, so my last part of this introduction is I want to talk about discrete versus continuous geometry. So I said that Riemann speculated about space-time being sort of discrete at a small scale, and of course we know that in quantum mechanics, that's the big problem of understanding the basic laws of physics. How do you unite quantum mechanics with gravity being described by Riemannian type geometry, Lorentzian geometry? And I just want to comment that there are two types of geometries that already exist that unify the discrete with the continuous. So Grothendieck was probably one of the greatest mathematicians of definitely the last century and maybe of all time. He had this way of thinking about a space. So I've written the formal thing there that a space is the same as a category of sheaves. But let me say what this means sort of in an intuitive way. The idea is that imagine you had some geometric space and you wanted to understand the shape, but it's dark and you can't see things. But you can only see, imagine it's like a stage and there are actors who can move around on the stage. Okay, so I learned this analogy from Kohn. And you see the actors moving around, and you have to deduce the shape of the stage on which they're acting from the way the actors move around and the way they interact. Okay, so that's basically what this is. This is saying that sheaves are some kind of mathematical objects that live on the space, and with which you can probe the space. And so his idea was that if you understood the way things interact in that stage, that's tantamount to understanding what that shape is, what that space is. And that, if you think physically, that's also what we are doing in physics. When you try to understand how things, matter behaves, you create space. You must have space and time to understand that. So that's a loose analogy, but this is a very powerful principle, and it's been used to prove amazing results. This way of thinking has been used to prove amazing results in number theory and various fields. And in this framework, the discrete and the continuous are on the same footing. Another comment I want to make is that there's a duality between geometry and algebra. So in physics, there's observables and states. And in mathematics, you can think of a space and the functions on it. And the most basic theorem that relates the two was this theorem by Gelfand and Neumark, which says that compact Hausdorff spaces are determined by the C-star algebra of continuous functions on them. That's a commutative C-star algebra. And this idea was taken forward by many people. So Grothendieck said that any commutative algebra should be thought of as a space, as an affine scheme. And he went on to build spaces by gluing affine schemes. And again, this has revolutionized modern geometry. Kohn, on the other hand, said let's allow non-commutative algebras, like the ones that occur in quantum mechanics. So you replace your commutative C-star algebra by a non-commutative C-star algebra, and you can consider all kinds of variants of that, and think of them as non-commutative spaces. Okay, and do geometry with them. And those ideas have been pushed very far. So I just wanted to mention these. And I'm mentioning these because the kind of geometry I'm going to talk today draws on this tradition and has a lot, I will be sort of motivating it by drawing pictures of string world sheets and so on. But it really comes from this, this way of thinking really goes back to Grothendieck. Okay, so good time to pause if there are any questions. Otherwise, I'm going to move on to talking about this equation. Okay, yeah. Well, that definition is quite technical. I mean, that's going to, I have to define what a sheaf is and I have to define what a category of sheaf. It's technical, but the analogy is what I explained. The technical definition I'm happy to explain after the, I think that, no, I won't need it today. This is just sort of, giving an overview to put us in some place. Now I'm going to go to something very concrete. So when you're saying in the context of the second point, so for example, arithmetic objects fit into Grothendieck's framework. So he can, in Kohn, yeah, so in context of Kohn's work also, there are lots of discrete objects which give rise to non-commutative algebras. I can give some examples. For the simplest example would be take a quiver, which is like a directed graph, and you can form an algebra out of it by taking parts in the quiver and multiplying them. That's not like the kind of things that Kohn typically looks at, but that would be an example. And if you look at its representation theory, you can treat it as if it's a space, as if it were a geometric space. And that's an example that even I will consider. But yeah, but he also considers all sorts of arithmetic examples that give rise to non-commutative space. Yeah. So, any other questions? Okay, so let's go back to this, to our favorite bagel, the everything bagel. And remember, it's a surface of a bagel, so it's a hollow bagel. And I just want to explain this equation d squared equal to 0. So you could do the following thing. You could take this bagel and cut it open along the two loops that I've drawn, and you would get this square. And I could chop up that square into two triangles the way I've done. And now the square, that picture is composed of various elements. It has zero-dimensional elements, like the point P. There's only one point P here. Then there are one-dimensional elements, the lines A, B, C. And then there's the two-dimensional things, the triangles. They're called simplices. So 0 simplices, 1 simplices, and 2 simplices. And given a simplex, I can take its boundary. So the boundary of a point is empty. The boundary of an interval is the difference of its endpoints. So in this case, all the endpoints, the differences are it's P minus P, which is 0. And the boundary of a two-dimensional thing will be, for example, sigma, the boundary is A plus B minus C, because you go around in some orientation. So you can now form, to take the boundary, I have to take formal linear combinations. And so I want to take formal sums of these things, and that's what I've written here. And there's a boundary map which takes the boundary of a formal sum of faces and produces a formal sum of edges and so on. Now here's something you can check. D squared is 0. The boundary square is 0. And that's, in this case, kind of trivial because the second map is 0. I just said the boundary of every edge here is P minus P. But I could have chopped up the triangle in a different way and put a vertex at the center. And now the boundary of this edge, for example, is Q minus P, so it's not 0. But even then, now in this case, you have a lot more simplices. So you have 4 2 simplices, 6 1 simplices, and 2 0 simplices. But you'll still find that D squared is 0. It's because every edge occurs with opposite orientation, occurs twice, and the orientations cancel out. Okay? So that's one example of how D squared equal to 0 comes up. Now, I want to use this equation D squared equal to 0 to measure the shape of the space. I want to measure the fact that, so when I look at this bagel, I see that somehow there are 2 loops, A and B, which seem to be preventing this thing from getting, being turned into a sphere, for example. Right? But how do I quantify that? How do I know that if this bagel was made of elastic and I could stretch it about, how do I know that I couldn't convert this thing into a sphere or into a sphere with 2 holes? So I need some way to quantitatively say that these 2 holes cannot be filled in. The disks A and B cannot, the circles A and B, the loops cannot be filled in. And the way you do that is to define this thing called the first homology of this thing. T2 is the bagel, surface of the bagel. And it's defined to be the set of one-dimensional simplices whose boundary is trivial. That's almost it, except that you have to identify 2 one-dimensional simplices if they differ by a boundary. So for example, A plus B and C represent the same one-dimensional object in this space because they differ by the boundary of sigma. A plus B minus C is the boundary of sigma. So if you impose this equivalence relation, you find that there are exactly 2 generators, A and B, for the space. Although we started with 3, A, B, and C, when you quotient out by this relation, you find there's only 2. And it turns out this is independent of how you chopped up that surface into triangles. So you can play with this, you'll find this always true. This is a question we gave our, so we were doing this math circles with school children recently, and this is elementary enough that you can just play with it. So it's actually a problem that we give them to try and figure out what happens when you chop up the square in different ways, and what changes, what doesn't change, and in particular, whether this changes. Well, we didn't define it this way. But now you could wonder if this is something special about the one-hole bagel, but it isn't. You can do this with a 2-hole surface, for example, and I'll let you look at this and convince yourself that you can, if you cut along A1 and B1, A2, B2, you will get this figure where that loop represents the line in the middle. And again, you can play the same game, chop it up into triangles, define the boundary, and calculate H1. And as expected, you would find that no matter how you chop it up, in dimension 1, you get 4 non-trivial cycles, 4 things that up to equivalence. And this Poincaré invented, and it's called homology. So this is the first homology of the surface, and it tells you that you can never turn this surface, for example, into the surface with 1 hole by just stretching it without tearing it. Now here's another way to think about this. So this was combinatorial, but here's another way. You can think of the surface of the bagel as obtained from a sheet of paper by rolling it up infinitely many times, and then rolling it up again infinitely many times in the opposite direction. If you do that, the square would be mapped 1-to-1 to this surface, except that the boundary edges would be identified with each other. Now, on R2, you have the coordinates x and y, so you have the differentials dx and dy. And locally on the surface of the torus, they correspond to the angular variables d theta and d psi. But the problem is that although x is a function, theta is not a function, because if you go around and come back, theta changes by 2 pi, so it's not really a well-defined function. And so what you find is that if you define the form that locally is d theta, so that's what alpha is here, alpha is locally dx or d theta, then its derivative is 0 because it's d of a function. When you take d squared of a function, it's 0. But it is not d of anything itself, because the integral of alpha around the loop is 1. So maybe you would have seen this as saying that if the gradient, if the divergence of a function is 0, then it should be the gradient. That's only true locally. It's not true globally. That's what this is saying. It's not true on the torus, for example. The thing that you learn in electromagnetism. So the failure of that result that you learn in electromagnetism to be true on the surface of a bagel is what is called DRAM cohomology. And again, you find that there are two elements generating DRAM cohomology, alpha and beta, corresponding to the dx and dy. Or on the torus, there are the variables d theta and d psi. And now let's try to understand this more systematically. So we can define something called a cochain complex. And all this is, again, very elementary. The VKs are just vector spaces. And D is just a linear map, so just a matrix. So cochain complex is just a sequence of vector spaces with a bunch of matrices, which I'll call them all D, such that D squared is D after D is 0. D times D is 0. And if you have such a cochain complex, you can define its cohomology, which is the set of elements in VK, such that its derivative dx, let's call dx the derivative. D times x is 0, but x itself is not D of something. So here's an example, which we just did. You take AK to be the set of differential K forms. So differential K form is something that you can integrate over a K-dimensional object. So it's something that looks like f dx dot dot dot. Mathematicians like to write wedge here, but you can omit the wedge if you like. dx1 wedge dxk. It's an object that looks locally like that, where f is some function. So those are K forms, and you can differentiate K forms. You simply differentiate the function like you would differentiate a function, and you use the rule that d squared is 0 and apply the Leibniz rule. That's it. So you have this exterior derivative, and then the cohomology of that is called the DRAM cohomology. So using this equation d squared equal to 0, we have a way to measure the holes in a space. I only talked about one-dimensional holes previously, but you can also measure n-dimensional holes or k-dimensional holes. Now you can do a slightly fancier thing with this version. So you can look at this differential forms and you can multiply them. You can take two of them and multiply them together to get multiply an I form and a J form to get an I plus J form. And so this makes this thing into what's called a differential graded algebra. In fact, a commutative differential graded algebra. So it's associative. The commutativity is what sometimes is called supercommutativity. I might have screwed up. It's not I. Yeah, it's I times J, sorry. It should be I times J. And it satisfies Leibniz rule. That's what it means to be a differential graded algebra. Now, here's the amazing thing that you might ask, well, okay, with this DRAM cohomology, I measured the holes. I could tell the bagel has 2 holes in it in dimension 1. But you might wonder, well, can you recover the space completely from it? And that seems really far-fetched, because just giving a 2-dimensional vector space and saying that something has 2 holes, and therefore it must be the torus, certainly seems very far-fetched. But the amazing fact is that if you're willing to compromise just a little bit, if you're willing to say that you consider spaces up to what's called rational homotopy equivalence, which just means that the following thing. So when you're studying spaces, you're looking at spheres in them, and you're interested in whether the spheres can be deformed away to a point. Okay, the things which measure this are called homotopy groups. And studying homotopy groups is incredibly complicated. So if you take a sphere, something as simple as a sphere, the homotopy groups of spheres are completely unknown. Okay? It's one of the big guiding problems of algebraic topology, is to understand homotopy groups of spheres. So that's an incredibly hard problem, beyond everything that we can access today. But here's a problem that's completely accessible, that if you declare that if sometimes it might happen that a sphere is not contractible, but 5 times the sphere is contractible. Just like in clock arithmetic, 12 is equal to 0, right? When you come around with the clock, come back to the start, 12 becomes equal to 0. So it might happen that a sphere is not contractible, but if you wrap around the sphere 12 times, it's contractible. Such elements are called torsion elements in the homotopy groups. And if you neglect all torsion, then you're studying spaces up to rational homotopy equivalence. And there's this amazing theorem that Quillen and Sullivan proved, or a bunch of theorems in the 1960s, which said that if you know the DRAM algebra, or if you know, like in the previous slide, we had a chain complex, A comma D, but it also has a multiplication, which makes it into an algebra. So they showed that spaces up to rational homotopy equivalence can be completely classified by cochain complexes with some algebraic operations on them. And in fact, the DRAM algebra completely determines the real homotopy type of a Kahler manifold, for example. But this is a much more general statement. So I'm not going to spell out what these algebraic operations are. They're algebraic operations very similar to the ones that I had on the previous slide. just a little bit more complicated. Now, I'll just take a moment to think how amazing this statement is. It's saying that you can reduce understanding all possible crazy shapes and all the ways that they can wiggle about and stretch and be deformed into each other by writing down a bunch of matrices, basically, because that's what this ultimately boils down to. It's a very complicated bunch of matrices, satisfying all kinds of constraints, but that's what it is. Okay, so I'm going to now jump to the string theory part, or topological string theory. So motivated by this, I want to study a space now. So now in the beginning of my talk, I had this picture of a point probe and then intervals, right? So the basic idea is going to be that instead of measuring our space around us with points, so imagine I had like a balloon here, a torus-shaped balloon, and it was completely dark, and all I could do was shine my laser on it. And you would look at how the laser moves around, and you would try to reduce the shape of the torus. But now imagine that the pinpoint of the laser wasn't a point, but it was like a loop or a string. And that loop or string is not like a classical loop or string, but it obeys some quantum mechanical laws. So it's somehow very fuzzy. That's the kind of picture you want to have in mind. And what we want to do is to study Kahler manifolds by mapping strings into them. And these strings behave quantum mechanically. Now, what do we know from the laws of quantum mechanics? If I have a string, if that's my elementary object, when I quantize, that thing should have a state which lives in some space. So it should have a state which lives in a vector space. Okay, and I'm going to just claim that in the kind of string theory I'm doing, it's going to be a co-chain complex, because I'm going to do something called topological string theory, but never mind. I'm not going to explain how I got there. It's a perfectly natural thing to do just by itself, mathematically. And now, whenever two strings collide, I should get a rule that combines these states and produces a new one. So I get a multiplication map on this chain complex, which I call M2. So my differential is called M1, and my second map is called M2. And here the picture just shows the string propagating inside this torus. And the rule is that the endpoints of the string have to live on some kind of object. They're called branes in physics, but they're just some geometrical objects. Okay, there's some geometrical objects on which the ends of the string have to be constrained. Just like when you do elementary classical vibrating strings, you talk about them being fixed at some points. It's something like that, except everything is quantum mechanical. But I'm not going to need any quantum mechanics in this talk. I'm just trying to motivate this for people who study these things. Okay, so, but it doesn't stop at M2. So if you look at this picture, these two pictures are pictures of the same process, because you can deform one into the other. Okay, so there's a map that corresponds to this picture, which I call M3, to the picture where I've straightened out the whole thing. And the left-hand picture corresponds to this M2 times M2 minus identity. The right-hand picture corresponds to this one. And the rule is that when you have this equivalence, the fact that you can deform this into this, that translates into the fact that the difference between these two things is D of something. Okay, so it's a co-boundary. And remember earlier, anything that's D of something is kind of trivial from our point of view. Right? We're killing off things that are D of something. So what this says is that the multiplication of this chain complex is not associative. So if I do A times BC, that's not the same as AB times C, but it is up to a term that's a boundary of something higher dimensional. So here's what an A infinity algebra is. An A infinity algebra is a graded vector space together with a collection of maps, Mn, like this. And I wrote a few equations, but here's all the equations they're required to satisfy. They're quadratic equations in these linear maps. And this structure was discovered by Stasheff in the 1960s, nothing to do with string theory in the physical sense. He was studying loop spaces of topological spaces, and he discovered the structure. So special cases of this are ordinary associative algebras, and V is concentrated in degree 0. And then all the Mn's are 0 automatically for degree reasons, except for n equals 2. And differential graded algebras, which is the case which I talked about earlier, where Mn is 0 for n not equal to 1 and 2. Now there's a geometric interpretation, just a fun thing, formal thing. You can interpret this as follows. You take the vector space V and you take linear coordinates on it, choose a basis. So you get some coordinates x1 through xn. This interpretation, I think, is due to Kontsevich, but maybe it was known before. And you can take formal non-commutative polynomials in these linear functions. Power series. formal expressions x1, x2, x1, x2 plus x3, and so on. Then giving the structure that I described, this whole infinite sequence of higher multiplications, is really the same as giving a single map Q from this algebra functions to the algebra functions, which is of degree 1, because everything here is graded, and which satisfies the equation Q bracket Q is 0, which is again Q squared equal to 0 in a certain sense. So the equation Q squared equal to 0 makes an appearance again. And the MNs can be thought of as Taylor coefficients of this vector field. If you write the vector field in local coordinates, it's nothing but the Taylor coefficients of that.
Hello. So that bracket that is defined intrinsically on the this power series, is that something? I mean, is it? I wanted to know: is there a freedom in defining that, or is it?
This one? No. So this one comes from the fact that I'm looking at derivations, meaning the vector fields. So they satisfy the Leibniz rule, and automatically you can check that if you do x. If, you can, the usual thing we do with vector fields, that the bracket of two vector fields becomes a vector field. So that's the standard. I mean, it's not something I have to make up. It's something that comes from the definition of being a derivation.
Okay, so it's the usual bracket, D bracket of vector fields on this.
I mean, you can modify the usual bracket. Maybe I think that's what you're saying, by adding like a term to it and asking for that to square to 0. Like I can start with Q and look at Q plus something, and modify this bracket.
So okay.
But that's a different. I'm not doing that here. I'm just picking the standard.
So when you say they are the same, that means when these two structures are the same, what you mean is that
if I write out this Q in local coordinates, in these coordinates,
okay,
then its Taylor component, it's the Taylor coefficients of that will be exactly these linear maps Mn. These Mn's are tensors with the same number of indices, and you can see that it will be this.
I see, and they obey these.
And this equation is just the equation Q bracket Q is 0.
0. Okay.
This is like when you write out everything in coordinates, you get this complicated looking thing.
Okay.
Okay, so okay, I'm going to run through this couple of slides pretty fast. So basically, in that previous picture, I had one boundary condition on which my strings could propagate, but I could have many, and I've drawn a few here, a few cycles. And in that case, the whole situation changes as follows. These things, I'm just calling them branes, you can call them objects. Then for every pair E0, E1, and so on, you have a cochain complex. And for every triple, you have a multiplication map. Earlier, I had a multiplication map V tensor V to V, and V was just C, this open string states from E to E. Now I have different boundary conditions, so I have many of them. So I have a bunch of different maps, but everything else stays pretty much the same. So what changes? An A infinity category instead of an A infinity algebra now has a set of objects instead of just one object, instead of just one brane. And for every pair of objects, it has a space of string states between them, or cochain complex. And then you have these higher maps as before, and they satisfy the same equation. Okay, so let me give you some examples of these infinity categories. So the one comes from symplectic geometry, and it's called the A model. So if you have a symplectic manifold, you can define what's called a Lagrangian submanifold. It's a submanifold such that satisfies these two conditions. Omega restricted to L is 0, and the dimension of L is half the dimension of M. What does this really mean? One way to think about it is if you think of the manifold as a phase space, then you know that you can't localize a particle to a point, right? Because of the uncertainty principle. So if you had a submanifold to which you can localize it, what would it look like? If you fix the x coordinates, then the momenta would be completely unknown. That would be an example of a Lagrangian submanifold. Similarly, if you fix the p's, then the x's are completely unknown. That's another example of a Lagrangian. So Lagrangian is something that generalizes these and is a submanifold. So it's not some fuzzy thing. It's like a submanifold, but it kind of fixes half the variables. Okay. So in a torus, anything is a Lagrangian because anything of dimension 1 is automatically satisfies the first condition. It's easy to check. Or for dimension 2 symplectic manifolds, every curve is a Lagrangian. And the A model category, so there's an A infinity category associated with this called the Fukaya category of M. And this is due to work of many people. I mean, it's a very, very long story in mathematics. It goes back to Morse theory, and then Floer generalized this to infinite dimensions. And Donaldson realized you could, Donaldson did some work that was kind of preliminary work, which went into defining the Fukaya category. And Kontsevich had, a lot to do with it, and so on. So many people contributed to it. And this Fukaya category, it's defined as follows. The objects are, it's very hard to define, first of all, I should say. It takes more than thousands of pages of mathematics to define the Fukaya category rigorously, okay? So anything I say is hand-waving, but here's the hand-waving picture. The objects are decorated Lagrangian submanifolds. And in fact, that's one of the big problems that the definition today, like a lot of people are working on, producing a clean conceptual definition of the Fukaya category. So objects are decorated Lagrangian submanifolds, and the HOMs is what's called the Floer complex. It's basically an infinite dimensional Morse complex. Okay, it's a Morse complex on the space of paths starting at the first Lagrangian and ending on the second Lagrangian, but all the problems arise because you're working in infinite dimensions. And MNs are basically obtained by these Taylor coefficients are obtained by counting pseudo-homomorphic disks with boundaries on these submanifolds. That's a rough idea. So that's from symplectic geometry. From complex geometry, also you can construct an A infinity category. If you have a complex manifold, you can define a category dB co of x. Its objects are the following. So my torus now I'm thinking of as a complex manifold. It has complex coordinates because it's covered by R2. In fact, it can be made into a complex manifold in many different ways. And if you were alert, you would have noticed that the first equation I drew when I was talking about Descartes and the analytic geometry was the equation of a cubic, and that is in fact the equation, the real points of an elliptic curve, which is whose complex points form a torus. So anyway, so the torus can be made into a complex manifold in many different ways, but let's take one of those. And what are the objects of this category? They are bounded complexes of holomorphic vector bundles. Now, what does that mean? That means that at each point of the manifold, I have a cochain complex of vector spaces, which varies holomorphically as I move the point, varies analytically as I move the point. Again, this is not cooked up. This is something, these objects have been studied for a long time in algebraic geometry because they're absolutely necessary to understand the geometry of the space. A third example coming from algebra. If you have a differential graded algebra, you can define this A infinity category PA, whose objects are pairs E comma E, where E is a projective module over the zero component of the differential graded algebra. And this math blackboard E is what's called a Z-graded connection. It's a map from E tensor A to E tensor A, which satisfies the Leibniz rule, is of degree +1, and guess what? Satisfies E squared equal to 0. So if you look at, if you take A to be the Dolbeau algebra of a complex manifold, you in fact recover the B model that I just described, the category, derived category of coherent sheaves on a complex manifold. Okay, so since I'm running out of time, let me move on to the last section. Now I told you in a compact Kahler manifold, sorry, I told you that if you have any manifold, you can measure the holes in it by this thing called the de Rham cohomology. But if you have a Kahler manifold, and if it's compact, so if it's like the one that I wrote down on the first, when I showed you the picture of that guy in P4, then it has what's called a Hodge decomposition, which is a decomposition according to the type of differential forms that I'm looking at. So differential forms in complex manifold can be written in terms of dz's and dz bars. And you say it's of type PQ if there are p dz's and q dz bars. And if you look at these differential forms, smooth differential forms, not analytic, and look at the del bar operator, differentiation with respect to dz bar, you can define a cochain complex whose cohomology is this HPQ. Now it's actually it might look kind of trivial, but it's actually a very deep fact due to Hodge. And it's a fact that has to do with the geometry of Kahler manifolds, that it satisfies this decomposition. So let me show you how that looks. So that means that if I write the dimensions of the cohomology groups, here they can be written as follows. H0 is H00, H1 is the sum of these two guys, H2 is the sum of the guys in the next row, and so on. So you can write this diamond. You can arrange those numbers into a diamond. So basically what we're saying is we can take all the holes in our space and somehow use the complex structure to decompose them into various types and arrange them in this array. And there are facts from algebraic geometry that tell you this array has this diamond of numbers has many symmetries. You can rotate it by 180 degrees and it remains unchanged, and you can reflect it in the vertical line, and that's just complex conjugation. It takes the PQ forms to the QP forms, so that leaves the thing unchanged. So here is the Hodge diamond of the picture of the variety that I showed you right at the beginning, the quintic. It's a Calabi-Yau manifold, whatever that means. I haven't defined that, and it looks like this. And there are its symmetries. And the 101 parameters here turns out, well, they measure some kind of holes in the space, but they also parameterize complex structure deformations of the space, the ways in which you can deform the complex structure on the space. And this is the deformations of the symplectic structure on the space. Okay. Now, I told you about the symmetries of the Hodge diamond, but there's an operation you can do on the Hodge diamond, which is rotated by 90 degrees. And you could ask, just for the fun of it, is there a space with that Hodge diamond? And there would be absolutely no a priori reason from pure algebraic geometry to believe that that is true, or that you can find such a thing. Can I have a couple more minutes? Or so yeah. So it turns out that string theory actually predicted that there should be some type of geometry that lives behind the rotated Hodge diamond. And they use that prediction to actually, they use that prediction to actually make mathematical predictions about enumerative geometry. So for example, you can take that space that I showed you, the quintic, and you can ask how many lines are there on that space? Straight lines. A line is a map from the Riemann sphere into that space, which is of degree 1. And it turns out you can count those, and there's 2875 of those. And you can ask how many degree 2 lines are there in that space, or curves are there in that space. And you can answer that question as well. And you can count those, and the numbers explode very rapidly and were very hard to compute. And physicists were able to compute them using heuristics from string theory. But it had no conceptual explanation, like a completely mathematical explanation about how to proceed in general. So Kontsevich proposed this thing called homological mirror symmetry, which says that if you're given one Kahler manifold, there is another, you say a pair of Kahler manifolds is mirror if the category I defined, the infinity category Fukaya of X omega, is equivalent to the derived category of coherent sheaves on the other guy. And the derived category here is equivalent to this Fukaya category. So the A and B models, these two categories get interchanged. The symplectic parameters on one side get interchanged with the complex parameters on the other side, right? Which is what also we saw when we rotate the Hodge diamond, but this is now a much more refined statement. And proving this conjecture, constructing X2 and proving HMS is a very active area of research, very well developed. There are entire programs now where people know how to go about proving this, but a lot of technology has to be developed. And now I think in a few years' time, one may expect that it will be done. So let me just run through this really quickly. So if you have an A infinity category, you can ask, well, now, how can I recover all the geometry of the space from that A infinity category? Well, I've only talked about open strings so far. I can also think about closed strings. It turns out that from this open string object, looking at the infinity category, you can construct something called the Hochschild chain complex, which is something you attach to the circle. And the way you do it, it's a cochain complex. I'm going to tell you what its n simplices are. Its n simplices are obtained by putting a copy of the open string state space here for every interval on the edge of the circle, and tensoring them all together on the circle. And the differential involves contracting adjacent strings, allowing them to collide and coalesce together. And the fact that they're on the circle is very important because you can also collide the last one with the first one. And you also see from this the manifest S1 symmetry, the circle acts on this. And that circle action is called Kahn's B operator, which was discovered in the 1980s, again, not with string theory, long before that. Okay. So for a nice space X, if you compute this Hochschild cohomology of the derived category of coherent sheaves, it turns out to be exactly those Hodge numbers that I told you about. So you can recover the geometry of a space, at least this level of the geometry, knowing the Hodge numbers. You can recover it from looking at this category, this infinity category. So this motivates, I mean, this and many other things motivates Koncevich's definition that a non-commutative space is a nice infinity category. And I haven't defined rigorously what nice means. That's a long story. Okay. And also, if you have two strings colliding or tracing out a worldsheet, for every such worldsheet picture, there's a map from the Hochschild cohomology of the category. Again, this, I should say, this Hochschild cohomology was known a long, long time ago, long before any of these considerations I'm talking about. You get a map from the Hochschild cohomology to this Hochschild cohomology. So these are some tensors in some vector spaces, and their components encode the enumerative invariants that I was talking about. The Gromov-Witten theory, for those who know what that is. Okay, so let me just finish with a couple of results and a question. So, you can ask, like, what does it mean to do geometry with these? I gave you one answer. You can recover some aspects of the cohomology, but you can do much more. So, for instance, you can start from a non-commutative space in this sense and construct a commutative space back from it. This commutative space is the moduli space parameterizing objects or branes in this non-commutative space. I'm not sure what the physics word for this is, but and when I say good, it's actually, well, it's something called a derived stack, which is a very complicated object, but has good theoretical properties. Okay, so that's a result of Tohen and myself from quite some time ago. Another question you could ask is, what's the moduli space of all these theories? What's the moduli space of all of these open string theories? And that's the same as asking what's the moduli space of these non-commutative spaces or infinity categories. And again, the first question to ask is, what does that moduli space look locally? And that is governed by something called deformation theory. And one can show that there's a reasonably well-behaved deformation theory, which again is all about the equation d squared equal to 0. So Lurie laid the foundations for this type of deformation theory following work of many people over many decades. And specific to understanding deformations of non-commutative spaces, Blank, Kazakov, and myself, we showed that is much better behaved than people worried about. I can tell you more about the challenges in the question answer session. Anyone's interested? So now here's the big question I want to leave you with. What is the non-commutative analog of a Kahler metric itself? I started this by talking about Kahler manifolds, and now I gave you a definition of a non-commutative space. And I want to ask, what is the non-commutative analog of a Kahler metric? And whatever it is, it should give you, now this is a bit technical, it should give you three things. It should give you a Bridgeland stability condition on the underlying category, a Kahler metric on the moduli space of objects that I just talked about, and a Donaldson-Uhlenbeck-Yau correspondence, which identifies polystable objects with harmonic representatives. And I should comment that I think string theorists already think in these terms, but nobody knows how to write down the equations for these harmonic representatives. I think not even the string theorists. So, so this is quite open, and this is something that we've been working on for several years. We have many exciting preliminary results which don't answer this question. Along the way, we just discovered all sorts of other interesting things about geometric invariant theory, which is the basic theory that you need to even start talking about this. Yeah, and then we have some preliminary results about this, some interesting analogies between different types of geometry and so on. Okay, I'll skip this slide. It's a summary slide. I'll just leave you with the summary, and I'll take questions. Thank you.
I don't know. Can I ask you to explain the last sentence? That it serves as a powerful language for quantum field theory and string theory.
Yes. So if you look at, you can take any quantum field theory. So here I was talking about something very specific. I was looking at topological string theory. I was looking at a sigma model in this particular story. But there's a much more general thing that if you take any quantum field theory and you look at the structure of the observables in that theory, let's take a topological theory to make life simpler. If it's non-topological, it's going to be that plus extra information. That's sort of what we're trying to do here with the Kahler. Then the observables form a higher categorical structure. So for example, the simplest example is if you look at observables and quantum mechanics, well, okay, that's not so high categorical, but topological. I mean, so the point is that if you look at observables, you can have observables concentrated in some region or localized at some point. You can have some observables at some other point, or maybe in a region. And you can, there's the OPE basically, which asks, when you put this into a bigger disk, or when you collide 2 points, what happens to those observables? The structure of that is exactly what higher category theory is about. Higher category theory is about studying the ways in which you can write multiplications. So usually when we do algebra, we write multiplication on a line, or we write all our operations on a line. But higher category theory is about studying operations parameterized by manifolds. And that's exactly what you study in quantum field theory. So the rigorous statement is that if you look at the observables in a topological quantum field theory, for example, they form what's called a locally constant factorization algebra, which is a kind of higher algebra. And the modules over that, which is what you'd want to study if you want to study the states in the theory and so on, they form higher categories. So the Hilbert space of an n-dimensional quantum field theory shouldn't really be thought of as a vector space. That's in codimension 1. But if you look at lower and lower codimension, then you find higher categories. And another way to say it is that you want to study extended operators in the theory. That's another way, maybe in physical language, that when you look at extended operators in all dimensions, the structure of that thing is a higher category. And if it's a non-topological theory, then it's actually much harder. It's even harder than studying higher categories. It's higher categories with some more data, I mean, more structure. That's kind of what we're doing with the Kahler geometry story.
The slide you had about the non-commutative analog of the Kahler manifold.
It's one of the one before.
The previous one, I guess, yeah. What I mean, I thought Kontsevich himself defined this notion of, at least where you have a Poisson algebra, you can consider the deformation of the non-commutative deformation of the functions on the space. That doesn't extend to directly to a Kahler manifold.
That's a different kind of non-commutative geometry in the sense that that's a. So if you have one of those kind of deformations, if you can start with a commutative Poisson manifold and deform it using the Poisson structure, which is like you still have a space with local geometry. You still have a space with points, and you're starting with something that's basically a manifold. So it has points and things like that.
Right.
And it has a notion of locality, and you're deforming the functions on that space. So if you now look at the category of branes on that space in the A model or the B model, you could ask, does that deform along with it? And it does. So in fact, the deformation theory, the deformation theory of so if you take C to be the derived category of coherent sheaves on one of these spaces, then its deformations are controlled by its second Hochschild cohomology is the tangent space of C, which splits as three things. It splits as Poisson deformations, so H0 of wedge 2 of Tx. These are Poisson deformations. Plus deformations of the complex structure. Plus deformations of, these are called Joby deformations. So basically what you're describing is if I take a commutative space and I look at one of these kind of deformations, then it would give me a deformation of the category. And I would have a deformation. I would have another non-commutative space. But this is completely different because here we're asking for something different. We're asking, suppose I have a category already given to me. What additional data do I need to provide on the category, which would remember the Kahler parameters of the category? So this category dB coeffects doesn't know the Kahler parameters. So we need to somehow put in the Kahler parameters in a categorical way. So I just give you any category. I don't know it comes from a space. I want to think of it as some fuzzy non-commutative space because the space can arise from anything. It can arise, for example, from the category associated to a quiver, as I was saying earlier. You can take a quiver and look at representations of the quiver. Take some quiver. And at each vertex, you put a vector space or a chain complex and so on. That gives you a representation. That's a very combinatorial object. it also gives me a non-commutative space, and there's no Poisson structure or anything there. And I would like to know what are the Kahler parameters, and there is an answer in this case, in fact.
So there's a Kahler structure in this particular case.
So in this particular case, if I assign a complex number in the upper half plane to every vertex, that gives me a Kahler structure in this sense on the category. And part of that is a theorem due to King. The last statement is a theorem due to King. That if you start with a quiver and you assign a complex number in the upper half plane to every vertex, you get a Kahler structure in the sense that I'm defining. But if you take, for example, a symplectic manifold, it is believed that if you provide a holomorphic volume form, like the Calabi form, that should determine the Kahler parameters on the Fukaya category. And if you give me the other one, if you give me the derived category of coherent sheaves, the choice of a Kahler form should determine the Kahler, this non-commutative Kahler structure. It's basically like knowing the deformed Hermitian-Yang-Mills equations, the stringy Hermitian-Yang-Mills equation, but nobody knows how to write them down for any. But what we have is a framework that doesn't use explicit PDEs, but uses the features of PDEs to kind of axiomatize what happens and try to capture it. Maybe I can say something further to your question. It's sort of what we're trying to do. I kind of like this picture. I think I put it into some of my talks sometimes. One way to think about, maybe the word emergent, I think Loga takes exception to that, but I think it's fine. But the idea here is that we want, so the A and B twists forget part of the structure. And similarly, if I have a Kahler manifold, you forget part of the structure. You can go to symplectic geometry or complex geometry. So the category that I construct, if I construct one of the categories, I only know one of the two things. And what we do know at the moment is how to start from an A infinity category. If I think of it as a Fukaya category, I know how to see features of symplectic geometry come out of it. And if I think of it as a derived category, I can extract features of a complex geometry. So given an abstract category, I can extract features of both symplectic and complex geometry. The question is, what is the structure? What additional structure do I put? So I can extract like the geometry of conformal field theory from it, at least part of it. I mean, I would say all of it. But we know that if you go to the boundary of the moduli space of conformal field theories, which should look like some collapse phenomenon where you get some kind of Riemannian manifolds. So in some limit. So whatever this is, it should be some quantum analog of like those limiting cases when various parameters go to 0. That's at least heuristically the picture. So that's what we're trying to do.
Yeah. So Ashwin, can you try once more, please?
Yeah. So am I audible now?
Now you're audible. Sorry about that.
No. I think the mistake was on my end. So yeah. So my question was actually about this slide. So is there expected to be a PDE that accomplishes the third bullet item, or is there no such expectation? Like you were saying, you were going to use some properties of PDEs, but not a PDE itself.
Yeah. So I can explain that. So I mean, let's think about what a PDE is, right? Like, so suppose we're looking at just a simpler thing. We're looking at the usual Hodge decomposition on an ordinary compact Riemannian manifold. And what we're asking is, if I have a differential form, which is closed, can I flow it down to a harmonic representative? And that's given by the heat equation, because the harmonic representative satisfies the Laplace equation. These equations are just nonlinear analogs of, there are some nonlinear analogs of that situation. So the abstract thing that you want is you want to minimize some quantity, and you want to do that by flowing down along the gradient of some function. Now, if you're in the complex setting, that might be given by PDE, but it's not clear for the derived category of coherent sheaves how to write down that PDE, except for very simple cases, except for line bundles and so on. I think Yao and his collaborators have spent a lot of time trying to understand the line bundle case, which is so far away from, like, there's line bundles, and then you can go to vector bundles, and then you can go to complexes of vector bundles, right? So there's some degrees, there's many challenges. But you could, if you're on the Fukaya category side, Fukaya categories a priori are defined over the Novikov field. So first of all, they're not even defined over the complex numbers. So even your notion of what a PDE is will have to be non-Archimedean in nature, because you're working over a non-Archimedean field. So the idea is, when I said abstract are the properties, what I meant is we need a process which minimizes a quantity and brings you to the critical point. Whether you describe that process as a smooth process where you write things in terms of partial derivatives and so on, which is usually what we call PDEs, or you take some kind of piecewise continuous path to come to the minimum, or you do something else crazy to get to the minimum, it doesn't matter as long as you get minimized and you get to the harmonic representative by some decreasing process, right? So you become much more flexible about what you mean by a PDE if your goal is to understand harmonic representatives. That's what I meant. I don't know if that answered your question.
Yeah, thank you.
Any more question from online audience? Please unmute yourself and ask a question now. Okay, there doesn't seem to be any more question.
I can ask one more.
Yeah,
sorry. When you said about the homological mirror symmetry, the conjecture of Kontsevich, which is now, so is the domain of this conjecture fleshed out? Meaning, does one know how general it is? Is it only Calabi-Yau manifolds? What is the most general?
So it's definitely gone. So in the beginning, it was Calabi-Yau manifolds. It's definitely gone beyond Calabi-Yau. So now there are for Fano type, which means, so Calabi-Yau would be like, for example, if I'm looking at a hypersurface, it would be hypersurface of degree n+1 in Pn. But if I look at things of degree less than n+1, those are Fanos. And for Fano manifolds, there's a very well-developed picture, which I think started out with Aru's work. But in any case, the idea is sort of that you reduce it. I mean, if you take a Fano manifold X, you can look at what's called the anti-canonical divisor inside it, which is a Calabi-Yau. And there's a relation between so on the B model side, the derived category of coherent sheaves, the B model of X restricts, I mean, whatever, there are functors going, there are maps going both ways. And you can study it by studying, there's a statement about homological mirror symmetry, which is now not about a single category, but it's about a category, it's a relative situation. It's a category with a map to a Calabi-Yau category. And on the mirror side, the geometry is a Landau-Ginzburg model. Instead of being just a space, it's a space with a function on it. And that again goes back to ideas of, I mean, in the physics literature, of course, the Landau-Ginzburg model. In math, it goes back to Lefschetz at the beginning of the century, where they studied Picard-Lefschetz theory. So a Landau-Ginzburg model gives you a map. Maybe I should have kind of a map from it's like Morse theory, but you are now mapping to the complex plane. So you have this superpotential W, which maps to C. And inside C, you have some bad points where the fiber becomes singular. And the idea is that you can, Lefschetz's idea was that you can understand the topology of the whole space by understanding the critical values, like in Morse theory, and understanding the monodromy around the critical values when you go around the critical values. And so now in what happens in homological mirror symmetry is you do exactly the same kind of thing. So you have this Landau-Ginzburg model, which is mirror to that Fano with anti-canonical divisor. So I should give you two categories, which are mirror to, so there I had a category corresponding to the Fano and a category corresponding to the anti-canonical divisor. Here I have a category corresponding to the smooth fiber, which I'll call, I don't know, F. Oh, let's call it, okay, F, and let's call it Y. And then I have a category corresponding to each singular fiber, let's call that X, corresponding to this particular singular fiber, X. And these are related by a pair of functors. So this category is called the Fukaya category, and this category is called the Fukaya-Seidel category of this singularity. And the objects in this category are thimbles, these things which are really important actually in understanding path integrals and so on. So you have these thimbles, and you can take a thimble and intersect it with the smooth fiber, and you can take a cycle in the smooth fiber and do an operation to it to get a thimble. So the mirror symmetry says that this pair is equivalent to that pair on the other side. For some, I mean, there's a prescription to construct these Landau-Ginzburg models. Yeah, so there's a prescription for Fanos. There's also a prescription for general type. I think Kazarkov and some others had some prescription, but I don't know the status of, I mean, how well developed that is. It's the other side, it's harder.
Okay, Doga?
Sorry, this is just regarding this objects of Hochschild, this HH spaces. Like, can you just tell me again how they come about from the point of view of A model or B model? Like, are they naturally coming out of them, or how are you building them?
No, I'm saying that you can take any category, any infinity category, or DG category, whatever, any of these categories, and there's a completely independent theory that tells you can build something called Hochschild homology out of it. It has a nice interpretation in terms of topological field theory, which is that picture I drew. You can think of it as like strings or something. But that's exactly the formula that Kahn and Sagan wrote down like in the 1980s. And now I'm saying if you happen to take the category to be the derived category of coherent sheaves, it will recover the Hodge cohomology that you study in algebraic geometry. If you happen to take, if the category happens to be the Fukaya category of some symplectic manifold, then that Hochschild homology is the symplectic cohomology of the space, which is some invariant in symplectic geometry. And in fact, you can recover, I only spoke about like sort of the tip of the iceberg. You can recover the whole Hodge structure and lots of things just by purely starting from a category and doing these abstract operations on them. And the intuition comes, it's not like it becomes more abstract, so it's like all algebra. The intuition comes from geometry, but you treat a category as if it is a geometric object, as if it's a manifold, basically.
Okay, just one more question. So if the A model and B models that you're taking are kind of dual to that, or they're, they're part of, they're related by mirror symmetry, they're exchanged by mirror symmetry.
Yeah.
Then is there something that you can say about the corresponding, Hochschild cohomology?
Yeah, absolutely. So the whole point is that if you have HMS, homological mirror symmetry, if you know the statement at the level of categories, in other words, if you've proven conservative statement, whatever program, if you've done this program, then everything else follows from it. So the closed string state space, everything you want to know about it, is a formal consequence. So you can, for example, say that the symplectic cohomology of, if you prove that the Fukaya category of this space is the derived category of this other space, then the symplectic cohomology of this space is the Hodge cohomology of this space, provided you've proven the theorem that I said, which took a lot of, people had to work on the symplectic side, had to work pretty hard for it. But now that it's a theorem, that's automatic. That's the point, that's the power of the non-commutative point of view, because you just have to work at this level. So ultimately, to answer Rajesh's question as well, ultimately mirror symmetry may be a statement about categories equipped with a stability condition. Stability being like Douglas pi stability parameters, and which interchanges the role of deformations of the, so when you take the mirror, deformations of the category should become deformations of the Kahler parameters, the stability parameters, and deformations of the stability parameters on this side should become the deformation of the category in this side.
But is there a way of understanding them without thinking about the open strings that you use to construct them? Is there a direct way to think a mirror symmetry relating just the closed string guy?
Yeah, so people before, HMS open string, the statement about categories is actually much harder to prove, generally speaking, than a corresponding closed string statement. So there are many cases where people verified things about mirror symmetry at the level of cohomology groups, which is the closed string statement, without knowing HMS to be true. A good example is the quintic itself. People have done lots of stuff about the quintic a long time ago, but only recently in 2017 did Ganatra, Perutz, and Sheridan recover all the calculations using HMS. But once HMS is proven in general, that will, there's a general program to prove it to say that here's an algorithm to construct a mirror and prove HMS for it. And once you've proven HMS, everything else follows for free. That's the idea.
Thank you.
Yeah. Let me ask a question which I have a feeling that it may be related to what you're saying, that you must be knowing about the conformal field theories in 2 dimensions, which central charge less than 1, right?
Yeah.
Can I continue with my question? Now, those conformal field theories are unitary conformal field theories. We know quite a bit about them. The neighborhood of the fixed points are well understood, etc. You can talk about a metric, which is called Zamolodchikov's metric around those fixed points.
That's exactly the part of the story, the scalar.
You can actually compute all the Betti numbers of this space of theories, which can be done. It's exactly known. So I wanted to ask you whether in your way of doing things, whether you can provide me with a metric on this full space of flows between these points and write down some sort of an Einstein type equation.
That's exactly,
say that those are the fixed points. So that was a big dream of string field theory.
Yeah, I mean, this is exactly, I mean, understanding the statements you just made, like understanding the Zamolodchikov metric is tantamount in this. I mean, what we're doing here is essentially understanding that, in a mathematical frame. I mean, this provides the framework to understand that systematically. It's similar to how like mirror symmetry was discovered in the early 90s, but it's still, there are many deep mysteries about it. It's not, I mean, it's one thing to say that you can, okay, there is some, you can exchange some generators in the Beresford algebra and so on. But it's another thing to say, if I give you a space, how do you construct the mirror? And how do you prove that the category of A-branes is the same as the category of, how do you show that everything matches up? It's at that level. So, I mean, the metric that you're talking about is exactly, as you say, it's exactly what's, entering the story here. But conformal field theories are not, the moduli space of conformal field theories and so on, that's not a rigorously, I mean, that's not a mathematically accessible object today, at least. So that's the problem.
What do you mean? I mean, what I'm saying is something very concrete, very explicit, which you can write down and
so what is the statement?
Understand. So what I told you actually about some aspects of this space of flows between these fixed points.
Do you mean you write down some specific conformal field theories, or do you understand?
No, we know all those conformal field theories, all of them.
But I think maybe there's a language. I mean, the thing is, when physicists say they know, it means something different from mathematicians.
No, I mean, we know means we know.
The classification of the conformal field theories with central charge less than 1. That's a discrete series.
Right.
That's the Katz and later that classification. So he is talking about the so-called flows that you can have, which take you from each of these discrete points. And these points are the critical points, and then there are flows between them.
Right, the RG fixed points, you're saying.
Yeah.
Right.
So for this category of CFTs, this is at least known at the physicist level of this thing, the properties of the space, its topology, etc.
So how do you, I mean, when you move away from the conformal points,
yes,
how do you map out the space of all QFTs?
What do you mean by that?
No, this is not in the whole space. This is only certain relevant deformations.
Relevant deformations.
Which take you from one to the next, to the next. There's a kind of a staircase. So
you fix two critical points and then you understand the
flows between them.
Between them, yeah.
But in between them, you're moving outside. Okay, I'd love to talk to you afterwards.
Okay, yeah, sure.
My feeling is that those objects in between that occur in between are hard to make. I mean, it may be possible to write down some Lagrangians and
no.
counter terms and so on.
Don't do all that. I don't want you to get into all that. I just want you to give me a metric or a Riemannian structure or a symplectic structure or whatever for this whole space.
But my point is that the space itself, you have to tell me how to write it down, and then I'll be happy to try to.
Yeah, just that's right.
Relevant deformations is like Morse theory. You look at the
exactly. I mean, that's what I'm saying actually. But we can discuss this.
Yeah.
There a question from Delhi.
Hello?
Okay, can I ask a question, please?
Yeah, please go ahead.
Yes, my question is, how does these complex transformations, has it been applied to any computational mechanics problems where highly complex geometries are involved? Like, for example, in CFD, can it simplify the Navier-Stokes equations? See, we use, for example, for transforming Cartesian system to a polar system or a spherical coordinate system. It is, in some cases, it simplifies the solution of equation. So, how about very complex geometries Like for example, the cardiopulmonary system geometry, if you want to do a computational fluid dynamic solution of cardiopulmonary system or a heart, just take the heart for example. Can this type of transformations help simplify the Navier-Stokes equations for and make it amenable for easy solution? I mean, what is the practical utility of this? Has it been applied? I'm asking about the practical utility of these complex transformations.
I think what I gathered is you're asking if there are practical applications. I gathered two things: that are there practical applications?
Yeah, that is right. Practical utility as far as solving computational mechanics problems in CFD or elasticity or whatever it is. Or electromagnetics.
Here's how I'll answer that question. Firstly, the Navier-Stokes equation is an incredibly hard equation, and I have nothing to say about it. Nothing at all. I don't know anything about it. But there are other experts here in the room. But when we, the way, I'm a mathematician, and the way we approach these things, we don't necessarily think of the applications. So I don't know what applications you have in mind, but I can maybe tell you just one or two fun things we discovered along the way. We found some interesting studying filtrations of objects in these categories and so on, some very abstract stuff. We found some description of these filtrations in terms of the asymptotic behavior of some ODEs. And those ODEs look very much like the kind of things people study in all sorts of applied fields like math biology and people who are studying machine learning, like that. I don't know much about those fields, but they have it has that flavor, and maybe somebody will pick it up someday and look at it. But yeah, I don't have anything more to say than it looked very similar to stuff that people.
But we can take one or two more. Okay, if not, let's thank Pranav once more for the interesting.